There we go.
You sympathize, is that what you're saying? Right, so so the third means of making alcohols is by reduction of carbonyl compounds. These are both aldehydes and ketones. So if you remember, a couple of days ago, maybe a little over a week or so, we looked at something called the oxidation profile of alcohols, which we're going to get back to today as well. And we said that if I have, for example, a primary alcohol, right, I can convert a primary alcohol, I can oxidize it into the aldehyde, and I could actually oxidize the aldehyde into a carboxylic acid. Right, so as we go this way, we are going up the oxidation ladder. And that's a term that's often used to describe it. We're going up the oxidation ladder. So I can oxidize primary alcohols to aldehydes and carboxylic acids. If I have a secondary alcohol on the other hand, I can oxidize that only as far as the ketone. And I will remind you that what makes an organic molecule, so at least in the oxygen series, what makes an organic molecule oxidizable is the presence of one of two substructures. Either I have what's called a carbonyl H, right? A carbonyl H, which is the H attached to the carbon, alpha to the OH, or having a carbonyl H. Right? So having either one of those substructures will make a compound in the oxygen series oxidizable. Primary alcohols have carbonyl H's. Aldehydes have carbonyl H's, so they're oxidizable. If I oxidize the secondary alcohol, which has a carbonyl H, I make the ketone, so nothing lives up the oxidation tree from the ketone, because ketones are devoid of carbonyl and carbonyl H's. If I have a tertiary alcohol, tertiary alcohols, you remember, are devoid of carbonyl H's. So tertiary alcohols are not oxidizable. Nothing happens when I try to oxidize a tertiary alcohol. So what we say is nothing lives up the oxidation tree from the ketone. Nothing lives up the oxidation tree from the tertiary alcohol. But redox can go both ways. So it means I can reduce an aldehyde into a primary alcohol. I can reduce a ketone into a secondary alcohol. Right? So if I take an aldehyde, I can go back down the ladder if I use a reducing agent, and I can make the primary alcohol. If I take the ketone and I go back down the ladder, I can reduce it into a secondary alcohol. There is nothing I can reduce into a tertiary alcohol, because there's nothing here to reduce. It also means that I can further up the ladder from the aldehyde, there's the carboxylic acid. So in theory, and we'll see that in a minute, I can actually reduce carboxylic acids down to the primary alcohol as well. So for now, we're going to focus on reducing compounds at the aldehyde level, aldehyde and ketone, to the alcohol. Specifically, the primary alcohol from the aldehyde, the secondary alcohol from the ketone. Good? So, we have a menu of reducing agents, and there are two that are useful for these reactions. So let's say I started off with methanol, or say ethanol. So ethanol on treatment with either aqueous sodium borohydride, that will work, or I could use lithium aluminum hydride followed by water. So this is called lithium aluminum hydride, which is abbreviated LAH. So LAH followed by water or aqueous sodium borohydride will reduce aldehydes into the corresponding primary alcohol. And just to make sure we understand what happened, what I've literally done is added H2 across the double bond. I put an H on this carbon and an H on that carbon. An H on this O. So H on the carbon and an H on the O. And that gives rise to the alcohol. Agreed? If I started off instead with a ketone, do we have this bit? Are we good here? If I started off with a ketone instead, then the reaction is very analogous. And what we get would be, let's say I started with acetone. If I treat acetone with either LaH followed by water or aqueous sodium borohydride, I would generate the corresponding secondary alcohol. And essentially what happened is I put an H on this carbon and an H on that O. Right? So just to, it would kind of look as if I did this. Right? So one H goes here, one H goes there, and I make the secondary alcohol. Okay? We want to talk a little bit about how those reactions happen, and to sort of compare the lithium aluminum hydride pathway against the borohydride pathway, because there are a couple little subtleties that are worth mentioning. So let's first of all see how those reactions occur. So first things first. You remember that carbonyl compounds, aldehydes and ketones, this carbon is sp2 hybridized, so it's trigonal planar, it's flat. Right? So the p orbital really extends, I'll draw it another way. The p orbital extends above and below the plane of the molecule like this. So this is my pi bond, right? That's my pi bond. So anything attacking an sp2 hybridized carbon in a ketone or an aldehyde or in a carbocation has to approach this way. There is nothing here for it. There's no orbital here to interact with. You want to remember that when you make a covalent bond, orbitals overlap. There is no orbital here. So even sometimes when we write mechanisms, I didn't do it here, sometimes when we write mechanisms, we draw crap like this. So we say, cyanide attacks here and the pi bond breaks. We do that with the full understanding this is not where cyanide attacks. It must attack from here or from behind the board because the p orbitals are perpendicular. Right? So when we're attacking the carbonyl compound, we must attack from either the top or the bottom so that my nucleophile is able to interact with the orbital. The orbitals can interact.